environment subcomponent, which is the physical environment, we move to the agent. So agent is the core algorithm which I was talking about, right? So this is the PPO agent. The agent which we are using is proximal policy optimization. This is a structure where it uses an actor network, which is the network responsible for taking an action or releasing water. We have a critic network, which evaluates whether action is good or bad. And this is separate from the evaluation which the virtual environment does. So once the agent takes an action, it goes to the reservoir takes a reward, gives a reward or a penalty, and this process continues. Why we chose PPO agent? It can handle continuous action space. So for example, you want to release water from a reservoir, right? Yeah, the release value can't be a discrete value. You can't say like, okay, I will just release 50 cubic or I'll release 100 cubic. No, it can be any value between a set limit. So the action space has to be continuous. This agent can take all relevant inputs like inflow, storage, evaporation, forecast, and provides adaptive and data-driven control. Eventually, this agent also learns anticipatory release pattern, which I was alluding to in the previous slide. It can balance the short-term demands. So it can guess or it can estimate that at the moment I need to release this much of water, but if I release this much of water, maybe in future there will be a drought condition. There will be a lack of water available. So let me release a little bit less, let me get penalized, but in future I need to. So it sees the long-term condition. It can basically prognose the long-term condition and see, okay, I need to hold this much of water because in future there will be a drought condition. So this is the advantage of using an AI agent. And fun thing, this is the same PPO agent which ChatGPT initially used. It's not the exact algorithm, but the similar algorithm which ChatGPT used to tune its large language model. So this is the agent which goes under the hood in ChatGPT. So as I was mentioning in this overall framework, the virtual environment consists of objectives and constraints. So we covered the physical environment component, we covered the agent. Now coming to the fun part, which is the virtual environment or the objectives. So in reinforcement learning, it's not like supervised machine learning where you're trying to meet the input, output, the prediction, find the loss between the prediction and the output labels. Here, what you're trying to do, you're telling the agent do something, and by means of reward, you communicate to the agent whether the actions it's taking is optimal or suboptimal. So one of the ways to communicate or to tell the agent that this is what I want you to do is by means of reward functions. So let's say my objective was to tell the agent that, hey agent, you release this much of water, but maintain the storage within the min and max storage limits. So min storage, the minimum storage in the reservoir should be 0.5 million acre feet, and the maximum should be 1.7 million acre feet. So the simplest reward, if anyone could think, is a binary step function, right? Like let's say if you keep the storage within these limits from 0.5 to 1.7 million acre feet, you get a reward of +1. If you keep the storage outside these bounds, you get a reward of -1. Okay, that's the simplest reward function someone could think. So slowly, let's say if I want to complicate the reward function, I'll go a step ahead and I would complicate it. Okay, I will give you +1 reward if you keep the storage exactly at the median of the min and max storage level. So 0.5 plus 1.7 million acre feet, the average of that would be 1.1 million acre feet. So if the storage is exactly at 1 point or close to 1.1 million acre feet, you get a reward of 1. And as you basically deviate from the storage, your reward starts decreasing. So that's a bit more complicated reward function, right? So we'll start with the results for that a bit more complicated reward function, and then I will show what a simple mathematical formulation can do to a big complex reservoir system. So this is the reward in this slide. The reward which we are using is the reward, this complex triangular reward, right? Where we are telling the agent, you try to keep the storage levels close to the mean of the min and max storage levels. Caveat here, the blue curve which you see on the left plot and on the right plot, those are historical storage and release values. And the point here is that this is not like supervised learning. We are not trying to match the historical storage level. That's just there for context, for people to understand how the hydraulic engineers or the operators are managing this reservoir. What we are trying to do is like we've just provided the initial storage value to the agent, and this was like these results are all testing data. So what the agent has to do is like once it gets its initial storage level, because of the reward function, it's trying to keep the storage level close to the mean of min and max storage value. As you can see, the orange curve, it hovers around the 1.1 million acre feet value. At least the agent is trying to do that. It's not trying to match the historical data. And to maintain that much of level, if you see the release pattern on the right plot, that's there, right? That's completely different from what we have the historical. So the point of the slide is that you can make the agent do things by means of formulating a mathematical reward function. So I mentioned the simplest reward function and a bit more complicated reward function, right? So here there's a comparison. On the left hand, we have the simplest reward function where the agent was told to maintain the storage within the min and max storage level. And on the right hand side, the agent was told to keep the storage within the min and max storage level, but at the same time, keep it close to the median or the average of the min and max storage. And you clearly see the difference. So just by tweaking the mathematical formulation of the reward, see how significantly the behavior of such a big complex reservoir system can vary. So that's the point I'm trying to make with the, like, you can make agent do things just by simply formulating the reward function. There are other ways of communicating to the agent, but reward function is one of the most direct and simple ways of doing that. Okay, so you saw the release pattern over here, right? This orange curve on the right-hand side plot. That's very wobbly kind of plot, right? The release patterns are very fluctuating. In the real world scenario, if the agent were to release this much of water suddenly, there will be catastrophe, right? There will be floods downstream. This is hypothetical in the simulation setup, right? Real world, we can't do something like this, right? We have to be careful. So can I enforce a smoothness? So now my reward function changed from keeping the storage close to the median of min and max storage. In addition, there's a penalty if I release abruptly. So now if you see, the agent is still following the constraint. It's keeping it within the min and max storage level, the storage, keeping it close to the median of min and max storage. But if you see the release pattern, that's quite smooth as compared to this release pattern, the orange color curve in the release plot. And if you see, compare it with this plot, it's completely different. And that's just by introducing a penalty for abrupt releases. This is a quantification of smoothness. Like, okay, if there's no smoothness and force on the agent, you have a wobbly kind of pattern. If you have a smoothness and force, you have pretty smooth release pattern. Okay, so we trained the agent and we tested it on our data, but just for our sake, like this is a very hypothetical condition. We wanted to check the robustness of the developed AI algorithm, because in the practical world where you have noisy data and this kind of robustness is kind of norm. Any AI algorithm without robustness to an unseen data is practically useful in the real world. You can't actually use it. It's good on pen and paper, training, testing, validation, but makes no sense in the real world. So what we did is we created a hypothetical situation. Already the agent was trained on a particular set. It never saw the testing set. This testing set is completely different. Here we changed the initial storage value. We amplified it by 50% above the max storage and 50% below the max storage. And still the pre-trained agent, which has never seen this data, is able to bring the storage between the min and max storage level, and it's trying to keep it close to the median of min and max storage levels. So this is what the agent is doing. And on the right side, we have the release pattern for this particular agent. So this is stress testing just to check the robustness of the trained algorithm. Apart from that, we performed several different stress tests where we, in the simulation, we basically enhanced the inflow by 25%, 50%, and 90%, more or less water available in the system. And still the agent, which is trained with a reward, where it's being told to keep the storage always between the min and max storage, is doing the task. So that's the power of the reinforcement learning agent we are using over here. Okay, so we saw this thing. It was all for the purpose of demonstration. I was showing the simple agent. In reality, what we are using, any reservoir is not a single task problem. It's always a multi-objective problem. And in fact, even with the multi-objective, you may have different streams in the reservoir. Let's say this diagram is just for illustration. Let's say there's an agent and there's a reservoir. It's the same Nehavo reservoir, but let's say there's a different stream of water, which accounts for hydropower, fisheries, and downstream ecosystem. And there's a separate stream of water, which accounts for the agriculture purpose. So the agent has to be multi-action. What we are currently building, and we have already built it, probably the software will be online probably in like next 2 months. It's like building a ecosystem of different agents. So each we are connecting different reservoirs in the continental United States of America, and each reservoir is having its own multi-action PPO agent. So each reservoir is being governed by an autonomous AI agent, and these all different reservoirs are connected. So each reservoir has its own agent, a multi-action AI agent, and these all reservoirs are connected. So I must say an ecosystem of multi-action agent, kind of agentic AI system. So if I were to show some results for this multi-action PPO, this is what's happening. So we have two streams of water, right? San Juan River release, and then we have the NIP release. It's still with the same objective. Agent is keeping the storage. The Q1 release, which you see, is the NIP or the agriculture release. Q2 is the regular San Juan release, which accounts for hydropower, fisheries, and downstream ecosystem. If you see these plots, what we see here is the actual storage. If you see, this is like an interquartile plot. The prediction made by the agent are in the light orange color shade. And if you see, it's still maintaining it within the min and max storage levels, but the variation in the predictions made by the agent are still much lower than what it was if you compare it with the historical storage variations. Apart from that, even with managing the storage, agent is able to generate much more hydropower than which was being historically generated. If you see the orange color shaded region on the top right corner plot, that's the historical hydropower generated when the human operator was operating it. The blue color shaded plot is the hydropower generated by the agent. So agent is typically generating more hydropower, which was historically being generated. At the same time, you see the plot on the bottom side, the blue color wobbly plot is agent is trying to meet the agricultural demand. So basically, a multi-action agent is addressing multiple objectives. And this is just one reservoir. We have connected different, like Lake Powell, Navajo. We have connected like different reservoirs, each having its own intelligent decision-making agent involved. So one of the things now, like I would like to take a step back and come back to the theme of this conference, right? Because my research bridges physics, data, and AI to develop intelligent systems that learn, adapt, and make responsible decisions in complex real-world systems. But what we have learned so far, right? Like I would like to take a step back from now. That was just the purpose of showing that intelligent AI for water reservoir was to make three, or I would say like 5 points quite visible, and which is like any AI needs physics. If an AI agent or an AI system is not physics aware, it's not going to probably work in the actual real world scenario. Besides that, one of the questions which I raised in the beginning of my talk is that can AI move beyond mere prediction task, which we already saw in the case of this reservoir problem, that AI can move beyond prediction. It's not just prediction. It's not like supervised machine learning. AI is making intelligent decisions. In the real world, if you have closely observed, any reservoir is a multi-action control. As we saw in this figure, there are like two streams of water. Actually, there are multiple streams of water. This is just for illustration. So that's a multi-action control. You have to take multiple actions at the same time. At the same time, this kind of complex big system is multi-objective. You have to manage storage. You have to generate maximum hydropower. You have to maintain water for fisheries. You have to address the agriculture needs, the demands by the farmers, demands by the municipalities, everything. So any system, such a large, huge scale system, it's always multi-action and multi-objective. So can an AI agent address this kind of problem? Because in the real world, most of the problems are multi-action and multi-objective optimization problem. Besides that, one of the important things which I pointed when I was showing the results for the stress test is that any AI algorithm, if you intend it to deploy in the real world, needs to be robust and adaptive. That's why we perform the stress test. Although the conditions may be hypothetical, like 50% above storage, water can never be 50% above storage in a reservoir, but it was just a way to prepare the agent for the worst. What if there's like too much of flood upstream, or there's too much of overflow of water? Then in that case, agent can work very fast and you can start releasing water not to overflow. Means the entire idea is our AI algorithm robust and adaptive? And that's the core. So again, apart from that, and we saw this AI agent can address all of these 5 points which I was mentioning. So in summary, I would say like the future lies in trustworthy physics-aware AI agents that work alongside domain experts to manage vital resources responsibly and build a sustainable future for all. So I would say this, and this closely aligns with the theme of your conference, which is like AI for sustainable and intelligent decision systems, right? So with that, I would like to thank all of you for your time and attention. I would also like to thank all the students, collaborators, and researchers who have worked with me. and the funding agencies and my industry partners who are responsible for supporting the kind of research I am pursuing. So I'm grateful to them. I've kept my LinkedIn. You can scan it, the QR code to connect with me. I would be more than happy to connect with young students, engineers, professors who are interested in AI, reinforcement learning, agentic AI. And again, thank you very much for the presentations, for coming here, for listening to this presentation. And I would be open to any questions if you have. Thank you. Thank you again.
Dear friends, if you want any question, if you have any doubt regarding this presentation about Shubhendu sir, क्या आप लोगों को कोई क्वेश्चन पूछना है? अभी सर ने जो आर्टिफिशियल इंटेलिजेंस एंड सस्टेनेबल एनर्जी के बारे में जो बताया, क्या कोई क्वेश्चन आप लोग के माइंड में है?
कोई भी डाउट हो आप लोग फ्री होके बताइए, कुछ भी हो क्वेश्चंस.
If you have any doubt, you can ask related to AI. Student also here, first year. AI students हैं? Yes sir. Do you know about the artificial intelligence, whatever presented by the sir, Shubhendu sir? Have you any doubt? कोई सवाल है? Yes, please. Sir, girl, what's your name, beta? Nazia. She want to ask a question with you, sir. Please, Nazia, come here.
Sir, I would like to question is that how much time it take to make it real?
नाजिया, कैन यू रिपीट? आप एक बार फिर से अपना क्वेश्चन रिपीट कर देंगे प्लीज?
सर, क्वेश्चन ये है कि इसको रियल में जब हमको एप्लीकेबल करेंगे उसको कितना टाइम लगेगा?
एक्चुअली नाजिया, ये हमने जो मैंने आपको रिजर्वॉयर वाली प्रॉब्लम दिखाई, तो ये ऑलरेडी हम किसी सिस्टम पे यूज कर रहे हैं. बट सारे सिस्टम पे, लेट्स से अगर मैं अमेरिका की बात करूं, तो हमारे पास इतने रिजर्वॉयर्स हैं, हमको कनेक्ट करना है. सो हमको पॉलिसी मेकर्स, गवर्नमेंट, लॉज, उनको भी कनेक्ट करना है. सो ऑलरेडी इसको हम लोग एक रिजर्वॉयर पे डिप्लॉय कर चुके हैं, टेस्ट कर चुके हैं. अभी जो प्रॉब्लम है कि हमें इसको सॉफ्टवेयर को रिलीज करना है, एंड इवेंचुअली लेट्स से अगर हमारे पास 1000 ऐसे रिजर्वॉयर्स हैं या डैम्स हैं और हमको उसको एआई से कंट्रोल करना है, तो हमें सबको कनेक्ट करना है. एंड उसके अलावा हमें सबसे परमिशन लेनी है. सारे गवर्नर्स, सेनेटर्स, गवर्नमेंट, लोकल बॉडीज इन्वॉल्व हैं. तो ऑल्दो हम गवर्नमेंट के लिए ही काम करते हैं बट सिस्टम ऐसे काम करता है. देयर आर स्टेट गवर्नमेंट्स, सेंट्रल फेडरल गवर्नमेंट, सो परमिशंस. एंड इसका बेसिकली आई वुड से कि अगर हमको इस फ्रेमवर्क को अगर आप ऐसे पूछ रहे हो कि इसको हमको डिप्लॉय करने में कितना टाइम लगेगा, आपको रिजर्वॉयर की डायमेंशंस पता है, तो हमने इस हिसाब से इसको बनाया है. और एक बार जब सॉफ्टवेयर रिलीज होगा, इट विल बी एन ओपन सॉफ्टवेयर. सो द थिंग इज दैट आप उसके डायमेंशन चेंज करिए, कुछ चीजें उसमें इनपुट आउटपुट होंगी. बहुत ही ईजी इंटरफेस है, आप उसको ऑपरेट कर सकते हैं. एंड कंटिन्यूअसली ये डेटा स्क्रैप करता है नेट से. जैसे जैसे आपका फीडबैक आएगा, ये एल्गोरिथम और इंप्रूव होगा. बट डिप्लॉयमेंट में टाइम नहीं लगेगा. टाइम इसका है कि एक्चुअली डिप्लॉय करने में जो परमिशंस चाहिए होती है, जैसे हमने एक रिजर्वॉयर, 2 रिजर्वॉयर के लिए ले ली, पर बाकी रिजर्वॉयर्स के लिए परमिशन लेने में हमें टाइम लगेगा. डिप्लॉयमेंट में इशू नहीं है. डिप्लॉयमेंट में ये है कि वंस यू नो द डायमेंशंस, आपको पता है कि उसकी वैल्यूज क्या है, वहां पे क्रिटिकल, एंडेंजर, लेवल्स ऑफ वाटर क्या है, आपको एक बार ये चीजें पता है, आप उसमें फीड करिए, सिस्टम आपके लिए उस पर इवेंचुअली सिमुलेट करेगा एंड देन वो स्टार्ट कर देगा रन करना. बट इंपॉर्टेंट थिंग है कि इसको हम विदाउट सुपरविजन नहीं छोड़ सकते, बिकॉज स्टिल ये एआई है. एआई इज मेंट टू कॉम्प्लीमेंट. हम एआई को हमको हेल्प करना है. एआई कैन नेवर रिप्लेस ह्यूमंस, बिकॉज हमारा भी इंटेलिजेंस इवॉल्व कर रहा है, राइट? इट्स स्टिल एन आर्टिफिशियल इंटेलिजेंस. हम लोग नेचुरल इंटेलिजेंस से गवर्न होते हैं. सो एआई के पास वो सेंटिमेंटल वैल्यू नहीं है अभी आज के डेट में. सो हम इसको विदाउट सुपरविजन नहीं छोड़ सकते. दैट्स द पॉइंट. थैंक यू. बहुत ही अच्छा क्वेश्चन था.
थैंक यू सर. Your answer was also very good, and I think हमारे स्टूडेंट्स को ये बातें समझ में आ गई हैं जिन चीजों को आपने बताया सर. And anyone more questions, students from your side? Anyone want to ask? No? Okay, sir. Students are very satisfied, and just I want to pay you a vote of thanks, respected sir, Shubhendu sir. It's my great pleasure and privilege to express my sincere gratitude to you for delivering such an insightful and inspiring keynote, sir, on the important topics, whatever you have presented. Your valuable insight, expertise, and practical perspective have greatly enriched our understanding of the importance of artificial intelligence and its role in building the society, in building the new era. On behalf of the organizing committee and KIPM College and all the participants, I extend our heartfelt thanks to you, sir, for taking the time with us, sharing your knowledge and experience. Thank you, sir. Thank you so much for your inspiring presence and for making this conference more meaningful and memorable, sir. So, lastly, thank you very much, sir.
Thank you.
अच्छा
Thank
लगा
you.
सर आपके साथ
Yeah.
करेंगे in future. Next, whenever we will conduct again any conference or seminar, then we will definitely connect with you, sir. Hope
Thank you.
at that time you will again with us, sir.
Thank you. Thank you. And I really enjoyed this interaction and I always love to be here. Like, yeah, thank you.
Thank you, sir.
Thank
Have
you.
a good day, sir.
Thank you.
Friends, आज का सेशन हम यहीं पे